We're going to use factoring to solve polynomials. Okay, that's what we're going to do. So let's go right to the next slide. So these are our steps. There's a couple steps here I'm going to have you write down. And honestly, you don't need to really write it down if you understand it already, but just for people that like steps. I know some of you like having steps. So the idea here is that if you want to solve an equation that's a polynomial, polynomial terms, right? Many terms. There are many terms in the equation here. What we want to do is follow a couple steps. And the first one is move everything over to one side of the equation. So the first step is to move all terms to one side of the equation. Move all terms to one side of the equation. Once we have that done, and everything's on that side, we can factor that side of the equation. So the side that you moved everything over to, we'll factor it next. Okay, obviously the side that has nothing left is a 0. You can't factor 0, so it's kind of obvious which side you're factoring. So move everything over to one side, so you have 0 on one side and everything else on the other, and then factor the side that has variables in it. The third step is to apply the zero product property. And I'll explain. You should know it already, but I'll explain further. Apply the zero product property. Now, first of all, who knows on the top of your head what was the zero product property? That was chapter 1 stuff, right? What's the zero product property?
Anything times 0 is 0.
Anything times 0 is 0. Agreed. So if I have a bunch of factors listed, hypothetically, right? X times Y times Z. Factors, X, Y, and Z. And those factors as a product equal 0. Which of them is 0? Is it X, is it Y, or is it Z? X, Y, Z equals 0. Which of those factors is 0 in that case? Any of them. Very good. Any of them is the answer. And that's what we have to remember to do this. Is that clear? Yes? Okay, so let's do this with an actual problem then. So the first problem we're going to look at here, example 1, says just to solve. So let's follow our steps. Step 1, let's move everything over. Move everything over. So it looks like I've got the x squared term already by itself. I recommend, write yourself a note please, write yourself a note. I highly recommend that you keep this positive no matter what way you have to. So if it started with a negative x squared, I would move the x squared over to the other side. Make x squared positive, life is always easier. So let's keep x squared on the left side, let's keep the 2x on the left side, and let's just move the 15 over. This is a simple example like I always start with the beginning ones. Step 2 says to factor it. Step 2 says to factor it. What do I have here? What do I have? Do I have a GCF? No. I saw a head shake. Right? No, I don't. Christian, what do I have here? Did you have your hand up? I saw a hand come up over there. Go ahead. Careful, remember, do the math. It has to multiply to this and add up to this. What numbers multiply to 15? And figure out how 5 and 3 give you 2. What should it be? Negative 5 and a positive 3. Good. Negative 5 times 3. Negative 5 and a positive 3. Okay, those values add up to negative 2 and then multiply to negative 15. Alex, you're going to keep going? Yeah. You want to do the last step? What do we do in the last step now?
Then you just do the 5, the T method, and then do 5 and negative 3.
Very good. So what did Alex do? He applied the zero product property. He said, you know what? If two things are multiplying, and they're factors, and they multiply to give you 0, well, if they give you 0, then one of them could be 0 or the other. But we don't know which one. So we make a little T-chart. Have you heard of this T-chart? It doesn't mean anything. Make a bunch of columns, right? The minute I have 3, 4, 5 variables, I'm going to have 5 columns and stuff. Each factor gets its own column in a sense. Or you simply set each factor equal to 0. No matter how many factors, if you have 37 factors, you set 37 things equal to 0 and solve for all 37 roots. Yes?
So if there is a GCF, like in the number on the outside of all of them, would that be a separate column too?
A number as a GCF or a variable?
Like, I don't know.
If you take out a 2, no. If you take out an x, yes. Variables, yes. Numbers, no. Okay? Now, I didn't use this phrase yet, and we didn't write it down on the previous slide because I want to talk first. The answers that make an equation true we call the solution. Another word for solution is root. Let's write that down, please. The roots of this equation are 5 and -3. Okay? Answers, solutions, roots. Same thing. Answers, solutions, roots. So if I say find the roots of the equation, it literally means find out what makes that equation true. And how do I know that this is right? I can plug these numbers back on in and check in the original. Okay? Theoretically, and you're going to see this later, we're going to also check numbers in the factor form. But because I did a lot of manipulation, I should check these in the original, back at the very, very top. Mark.
So it would be x equals 5 or x equals -3?
Correct. Is that your question?
So if you wrote it with and, like 5 and -3.
It's honestly, it is interchangeable in the sense that it doesn't matter right now. Okay, but technically speaking, it's one or the other. It's one or the other. Okay, but I'm not going to dock you points for the word and in that case, okay? Because this solution works and this solution works, but they work separately, right? If you apply just one of them. I can't put 5 in for x squared, right, at the top, and then put the -3 in for x and expect it to work. They don't work together, they work independently as answers. They're not coupled, is the phrase we'd say. All right, so let's go to the second example to see this again. So just a little bit more complicated. Based on what I told you, and I gave you a little hint, how would you start this problem? How would you start this problem, Eduardo?
I would move the 10r and the 8 over, and so it would be -3r squared plus 10r plus 8 equals 0.
Okay, but we wanted a positive coefficient to lead, so what would you then do if you did that? Multiply everything by? By -1. So that's one way to do it. Can you rethink that now, based on what I was just saying, and think about another way to solve this? Instead of moving the other way, let's move the other direction.
You can just move the 3r squared over.
Yeah. Let's do that. It's the same thing, really, but I want the r squared to be positive, so I'm just going to move it over, and it's just one step. Is that agreeable? Is that reasonable? It just makes life easier when you factor. Because if you have a -3r squared, then AC method gets a little more complicated, and your factors are -3r and then r, and then it gets a little bit messy. So it's just easier when my leading coefficient is positive. I'm just being honest with you. You can do it either way, but it just makes life easier, and you want to take the easier route. So here, I want to use AC method, right? So on the corner, let's list AC. AC is going to be -24. And then we have to ask ourselves, what numbers multiply to -24, it's a positive and a negative, that give me a sum of -10. Remember, AC method now, we don't look to see what multiplies to this and adds to this. We say what multiplies to this and adds still to this. So what multiplies to -24 and adds to -10? Yeah, a +2 and a -12. And notice where I'm writing these numbers on the right over here. I'm doing this for a reason. I want you to see that these are not my factors, right? This is what we're going to break up the middle term into. Go back to AC method if you forgot how it works. We're breaking the middle term up. So the equation remains the same except for the middle term. And I'm going to break the middle term into +2r and a -12r. And realistically, I can see that mathematically, this is still true. Because the -10 is really the sum of 2 and -12. That's what -10 is. Why did I do that? Why did I do that? What was the reasoning behind that? What did it create an opportunity for? What opportunity? I should have saw every hand shoot up as soon as you see this. What opportunity exists now? What opportunity exists? What do you see happening here? Helen, what do you think?
You can factor out
By what method? What method do I use? Yes, you're right. Yes, but specifically when I see 4 terms, I might say factor by what? Grouping. 4 terms, a lot of you struggled with this on the test. There were 3 examples of factor by grouping actually on the test. Factor by grouping is obvious when there are 4 terms. That's why breaking up the middle term makes it factor by grouping, right? So you're doing that automatically. It doesn't matter which way you write the middle terms. Remember, we showed it doesn't matter if you write negative 12 plus 2r or a positive 2r plus negative 12. So I'm going to go ahead and put my little dash line here to represent, that's the split. I go ahead and look here at the first half of the split, and I say, what's the GCF right here? What do I get? What's the GCF in the first 2 terms? R. Leaving behind?
3r plus 2.
All right, I agree with that. That's the first 2 terms. Now, if 3r plus 2 is my leftover, what's left over on the other side? What has to be left over for this method to work? 3r plus 2. It's got to be. If this is not the case, this method isn't actually working. Still got to put equals 0 on the left. What comes out of those 2 values here that gives me 3r plus 2? Negative 4. Very good. Negative 4, not just 4. Got to take out a negative 4. Now we recognize that 3r plus 2 is actually a GCF of both of these terms, right? This is term 1 right here, this whole thing. This is term 2. And these are GCFs because this is in both terms. So I can take 3r plus 2 out in front. And when I do that, I'm left with r minus 4. So for those that struggled with AC, here's another review of AC method. Really trying to drill it home to you now that factoring will never go away. I'm telling you now, if there is something as an Algebra 2 student that you have to be a master of, as an algebra student in your middle school, you really want to be a master of linear functions. That was the goal, whether you realize it or not. Algebra 1 and basic algebra linear functions is what you want to be a master of. Algebra 2, quadratics, anything with factoring. Polynomials in general is what Algebra 2 is really all about. When you get to trig, you're looking at triangles, angles, measurements, right? Sine and cosine waves. When you get to pre-calculus, you start to look at things like limits and values and concavity. When you get to calculus, is the big picture of everything. But this is used all the way through calculus and beyond. You got to be able to factor. Okay, so make sure that if you're not sure about this, that you definitely come see me during a free so that we can go over some more examples together and maybe clear it up. Now here's the tricky part. Some of you might just give me answers of negative 2 and 4 right now. And that's not right. Negative 2 is not correct. 4 is correct, and 4 comes from this right here. Alex, what's the other side?
Negative 2/3.
Good. And we have to remember to set the whole factor equal to 0, so it becomes 3r equals negative 2, or r equals negative 2 over 3. So those are my 2 answers for this problem. Those are my what again? What's the word? What's the word? Roots. Those are my roots to this equation. My roots to this equation. Questions so far? A lengthier problem just based on the nature of the factoring involved. As the factoring gets more difficult, the problem just gets a little bit trickier. But this is literally nothing new when it comes to 4, 5, 4, 6. It's the exact same factoring you did. But now it's just set equal to 0, and it's in an equation where we're solving it. So this is not any more difficult than 4. I actually find the students do better on this because it's like the 3rd time they're factoring now. So by this point, it's like if you don't get AC method, you got to actually make sure you learn it, right? So you just do so much factoring by this point that this seems to be the better results on tests, or at least this. One more, and then we'll get into something that's a little bit trickier, I think, with example 4. Do I start? Oh no, example 5, I start with the trickier stuff. So let's try and fly through 3 and 4. For 3, I'm going to move things over. I'm going to put it in order. I'm going to recognize here this is a special case. The factors are both x minus 5. If I didn't know that, I could actually just factor it, which gives me 2 answers. But those 2 answers happen to be the same thing, right? So what do we say here? What do we call this? Anybody have a phrase for this that they've learned in their math class?
A double root.
Good. Double, or in general, repeated. Because it can be a triple root, a quadruple root, a quintuple root, etc., etc. So it's a repeated root. This, yes, Alex, is a double root. This is very important that we recognize and identify it, because on a graph, roots look different. If it's a regular root, it looks like one thing on a graph. If it's a double root, it looks like a totally different shape. If it's a triple root, it looks even different. So what we're going to talk about later in the year are shapes of polynomials and graphs. We're going to get to that toward the end of chapters 6 and 7. Okay? We're going to get into that stuff. So we have to consider that and remember that this is called a double root. So you could just say x equals 5. And you could write here that it's a double root, or you can write, some books write multiplicity equals 2. It's an old way of saying it. It's kind of like not used right now anymore. Multiplicity, how many times the root exists. So multiplicity equals 2. All right, so look at the fourth example here. In the fourth example, it looks a little bit complicated at first, because it looks like, you know what? This is factored already, right? There's a 2x minus 1 and a 4x. It looks like it's factored. So why don't I just move everything over and set it equal to 0? And this is the first thing that 9 out of 10 students will think to do, which is correct. You can move the whole thing over. All right, so that's a good starting point. But the problem on tests is this. I then have students that think that these are factored, and they're not factors. Okay, everybody see the minus sign right here? This means that this is a term, and this whole thing is a term. Within this second term, there are 2 factors. But we cannot use the zero product property, because that only works if everything is factors. And we have, again, term A and term B. We do not have factors.
So you have to distribute the negative 4x. And then
Go ahead, what does it become out? Keep going.
it would be negative 8x squared plus 4x. And then you can distribute out an x from the whole thing.
Oh, what's the word for that? Distribute out?
Or factor out.
Factor out an x. Does everybody see what Alex is doing now? After distributing, he recognized, oh, there's x in everything. Let's take an x out. I agree. Leaving me behind with?
3x squared minus 8x plus 4.
And now I can factor this. It's messy, but I can factor it. Okay? It's another AC method example. It's another one just to kind of drill it home into your head.
So like before, I first thought that like you distribute before x into the 2x minus 1 before you.
You could do that. That's fine. Yeah, absolutely. If you want to distribute the 4x first and then move the 2 terms over separately, you'll get back to what you had here, right?
Yeah,
and that's
but
fine.
I have negative 4, not positive 4. Like I probably just messed up.
Yeah, check your work, because it looks like the 4x times the negative 1 will be negative 4x, but then you have to move it over as a positive 4x. Yeah?
How would you go on from there? Would x be equal to 0?
Yes, very good, because that's one of your factors. So to continue this problem, I have to consider that this factor is like that, right? That's what it's going to become, which makes me have a 3-column t-chart now. 3 factors, 3 columns. That's what I was referring to earlier. You always set each factor equal to 0. So the first factor is x. So you know what? That answer is done. X equals 0 is the first possibility, and that makes sense. Because if x is 0, everybody look up here, put a 0 in. What do these all go to? And 0 equals 0, right? So 0 makes sense. The other 2 answers come from my factors that I have to come up with still. I know it's going to be a 3x, and I know it's going to be an x. I can sit here and do trial and error because it's 4 and 1 or 2 and 2. Right? This is going to be 4 and 1 or 2 and 2. Probably both going to be negative to give me a negative on the inside. So I know that already. I can kind of deduce that this is the answer, either with a 1 and 4, a 4 and 1, or a 2 and 2. I could sit here and try. It's 3 possibilities. You could just try them out. Or you could use AC method. What does it come out to be?
2 and 2.
2 and 2? And if you did AC method, that's what you end up getting probably. But again, because of the fact that this was a negative and this was a positive, the only way to get things to multiply to positive is if these are the same sign. So either they're both positive or both negative. But since this is negative, these have to add up as negatives to become more negative. If I did 4 and 1, it doesn't work. Let's see. 3 times 2 gives me negative 6, and negative 2 is negative 8. So it works. I can do a quick FOIL using outer and inner to see if that works out. So my answers are going to become 2/3 and 2. Okay, those are my additional answers, I should say. I have the 0 already from the previous one. So you have 3 answers. What was the degree of this polynomial?
3.
3. You have 3 answers, the degree was 3. The last example, how many answers did we get? 2. What was the degree? 2. So what are you putting together? Make a statement, please.
The number of,
Solutions, roots.
yeah, is the number of degrees.
Yeah, is equal to, at most, the degree number. We're going to learn later, bless you, or whatever that was. We're going to learn later, it looked like you were about to sneeze, you went like that. That the answers can also be what's called imaginary. But for now, don't worry about it. But we will get into that. Okay, and that's when we have like 2 imaginary answers and 1 real one. And we'll still have 3 answers though, right? Because it's degree of 3. So we'll see that the degree is the answer that, or the degree is the number that limits how many answers you're going to have. Restricts it. So number 5 here, before we get into it, I quickly talk about the idea here that I want you to start considering functions also. Okay, I want you to think about functions themselves and saying to yourself, what is the 0 of a function? Have you heard that phrase before? When somebody says, find the zeros of a function. Find the zeros of a function. What are they actually asking you to do?
The x-intercepts.
The x-intercepts. Let's write this down at the top before we even do this example. Zeros of a function mean set the function equal to 0, which gives you the x-intercepts. When you're finding the 0, I just want to word that properly, sorry. When you're finding the zeros of a function again, you're really just setting the function equal to 0, which is what Morrell said by saying, you know what, find the x-intercepts. And when you find the x-intercepts, what's your rule in math to find intercepts? If I want the x-intercept, I should. And if I want the y-intercept, I should. So I always set the opposing variable equal to 0. So if I'm trying to find out when the function f of x, or y, or in this case h of k, when the function is 0, I set the function itself equal to 0, put a 0 in here, and then solve like I did before. So zeros of a function are the same thing as roots of an equation. Do we see the connection here? Because what I'm doing next is this. Finding the zeros by setting the function equal to 0. AKA the x-intercepts. So the roots of an equation are the same thing as the zeros of a function or the x-intercepts of the graph. Those phrases I'm using are all interchangeable. We should probably write the fact down, right? The percentage really. The x-intercepts of a graph is the same thing as the zeros of a function, which turns out to be the same thing as the roots of an equation. And we set that equation equal to 0, which is what we're doing here. What do my answers to this become? What do my answers become? First of all, how many factors do I have here? How many factors do I have?
2.
How many factors do I have? Alex?
3.
Not 3, no.
Oh, 5.
One more. 6. You have one of the first.
Okay.
You've got a double factor here and a triple factor here. They're the same, but they're actually factors. So when you see this, you need to start visualizing this. Right? This is what you have to visualize, okay? Obviously, you're not going to write this out. This is a waste of time. Okay, for now, you can write it out. But I mean, on a test, you don't write all that out. But you need to see that in your head when you see an exponent outside of a binomial. The exponent simply tells you how many times that factor is repeated. Yes? No, you don't have to. It's going to be messy if you try to go ahead and multiply it out. It's all right. It turns out you'll get a really long polynomial with k to the 6th power, right? Yeah, but you know what? Remember, the whole idea Helen, is to find the factor form and then get the answers, right? So multiplying it out, you're going to have to refactor it, which is probably pretty difficult to do. So I would not multiply it out. I would solve it at this stage. I would say, you know what? These are all going to give me answers. Again, I would never really do this. You see what I'm saying? I would not write this out this many times. I would simply write that K is the solution set of 0, 1, and negative 2. Because your repeated roots you have to write several times. If we're graphing it, it's important to recognize, though, the multiplicity level. Triple, double, single. Right? Single root, double root, triple root. That's all we're looking at there. I want you to see the idea that we could have several of these in multiplicity. How many examples do I give you total? I just want to get time-wise. 8? Okay. We're doing all right. Carry the next one. I'm trying to make these problems as varied as possible. What's my automatic first step for these problems? Make life easy on you. The zeros of any function, what's the first step? Regina?
You set the equation to 0.
Good. Okay, which is the thing that most people forget about. Set the equation equal to 0. And the second step, Regina? And this one? What would you recommend I do for a second step? Yeah, I could. Francisco? Multiply by 10 here. Everything. Because if I multiply 0 times 10 on the left, what is it still?
0.
Yeah. So I can multiply everything by 10, and it just makes life a little bit easier on me. Okay, just to give me integer coefficients. That's the only reason. And then yes, so Regina, to answer your question, you could have used AC method when it's in decimal form if you wanted to. It's just easier like this, right? So we list AC. AC is 10. What multiplies to give you 10 and adds up to negative 11? Yep. Negative 10 and negative 1. So let's break up that middle term into negative 10x and negative 1x. GCF of the first two terms. GCF of the first two terms. 2x, very good. Okay, if I take that out, I'm left behind with x minus 5. So is that going to work on the right side? What do I have to take out to get x minus 5, Julia? Good. Take out a negative 1, and you're left with x, and then a minus 5. Again, x minus 5 is now my GCF, because it's in both terms. So I take x minus 5 out in front. And what does that leave me behind with? 2x minus 1. So my zeros of this function are 5 and 1/2. If you're struggling to get that last step, set each factor equal to 0 in your head and solve. Regina.
I did 2x squared minus 1x minus
Yep.
10x plus 5.
So you get the same answer.
I got
Your repeated guy should be 2x minus 1 in both these spots. This should be 2x minus 1, and this should be x minus 5. Do you see how they switch spots? Did it work or did it not work for you? If it didn't work, it means there's probably a small mistake somewhere.
Yeah, I messed
Got
up.
it? Okay, so it's going to work, it's just going to be, they're going to be opposite each other. All right, so again, pick up on the fact that I can multiply by 10, it doesn't change my roots. Can I quickly show you something? You're not held responsible for this yet. We're going to get to this later in the year. But, just so you're aware, this has x-intercepts, we said, of 5 and 1/2. Those are the answers. So I can tell you already that this graph looks like this. All right? When we multiplied by 10, I want you to see this, so please look up. This is the original graph. That's the original function, g of x at the top. When we multiplied by 10, we stretched the graph, actually. But it keeps the same x-intercepts. So this graph this equation here as a function is what you're seeing there in black. In blue, from this right here, or even from this in red, I should say, in red, it would simply look like this. It would just be stretched out a lot more. But they have the same x-intercepts. So that's why we're allowed to multiply by 10. Even though it looks like what's in red here would be a very different function on a graph, than what's in black, they share the same x-intercepts because they're multiples of one another.
How do you know that it's an upward facing one?
Because it's a positive leading coefficient. We're going to talk about that a little later, okay? The negative leading coefficient indicates downward opening, called concave down or concave up. I want to get to these, so let's take a quick look. This says, where does it cross the x-axis? Which means it's saying, what are the x-intercepts? Which means it's saying, what are the zeros? So this is the same problem inherently as the last ones. But what's the major difference here? It's not x squared anymore. What is it? Yeah, so when I factor this, instead of this being x and x, what are they going to be, Alex?
X squared.
X squared and x squared. Because what's x squared times x squared? X to the fourth. Back to what we had. Thank you. Now, treat it like the other problems. What multiplies to negative 20 and what adds up to negative 9? Same factoring technique outside of this. My answers are?
Negative 4,
Negative 4, negative
negative 5.
5. Negative 4, well, look at that. This is really just difference of two squares. And then the other one I can't factor any further. So take a look at what I did. I factored this from difference of two squares. X squared minus 4 can get further factored. How many factors? I see only 3. But how many solutions will there be? Look at the degree of the polynomial. How many answers are there going to be? It's going to be 4. 1, 2, 3, 4. I want to quickly show you that. Those are easy. We're done, right? Those are the easy ones. You should be able to do them. The third part, take a look, please. We set the factor equal to 0, move the 5 over, and then take the square root. You get plus or minus radical 5. So there's 2 answers. There's 3, and there's 4. Again, you have to move the 5 over, and then you get x squared equals 5. When you take it, we're going to talk more about this with roots and stuff, okay? When you take a square root, just write yourself a note. When you take a square root, when you're solving an equation, your answer is always plus or minus. There's 2 answers. So my 4 x-intercepts for this graph, are negative 2, 2, negative root 5, and root 5. Oops. Okay, those are my 4 zeros of the function, or x-intercepts, or roots to the equation itself. Roots to the equation. There's one more. We're going to run out of time. I want to see if it's worth... Okay, here's what I do, because you're going to run out of time in a minute. Please take a look at this tonight. Recognize there are 4 terms. What does 4 terms automatically trigger in your head?
Factor by grouping.
Factor by grouping. So move everything over, please, and try to factor this by grouping tonight. It will work, okay? I promise it will work. It's going to be messy. Your answer is going to be like x equals 2a or 2b. There's no numbers here. It's going to be a's and b's in your answer. So practice this tonight. Look at the notes or look at the video for the last part of it. The bell's going to ring in a minute. But I do want you to take a look at the homework, please. Okay, so definitely look at the homework so that tomorrow when you come in, you have any questions on this, we can definitely look at those. It's a C day, so I got to decide if I want to make it maybe a day where you guys work together in groups on part of the project work or continue. I might go right before 8. I got to think about it tonight. Okay, we'll do this, please, tonight. Either way, do this. You're welcome. Oh, thanks. What are you studying right now in math? What are you studying in math right now?
We just started following them.
Good. But the ideas are the same still. You know, you learn the same topics, then you just kind of make them a little harder. Good. Nice. Thank you for coming to visit us.